Hello guys. So today we'll be treating joint variation, but then I'll be treating combined variation on this slide. So let me quickly go through what joint variation is. Joint variation is more like you talking about direct variation, but in joint variation you could combine two variables together, as in one could say x varies jointly as the square of y and z. So they have to be joined together. Y squared and z would be taken as one. That will be the product of y squared and z, and that gives me x equals ky squared z. Or you could say x varies jointly as both y and z. That gives me x equals ky and z. So it's as simple as that, and then you key in your formula, get your k, and that's how. It's very easy. It's just like direct variation, but today we'll be going to combined variation. So here in combined variation, it's also very easy. But in combined variation, you can combine two different variations together. It's either you combine two different variations together, or you combine the same variation twice, but this involves more than two variables in combined variation. So let me read from here. It says this is as simple as solving direct and inverse variation, but here we'll be having more than two variables that vary across each other. What this simply means is that we could have a direct variation varying across a direct variation, and at the same time varying across another direct variation, or varying across an inverse variation. So I have it here. I can say x varies directly as y and varies directly as z also. Or I could say x varies directly as y and varies inversely as z at the same time. So can you see the difference between these and those ones we've been doing so far? So just let's check out some examples to know how to solve them. So let's see some samples. So here we have it says x varies directly as y and directly as z also. When x is 3, y equals 4, z is 5. Find the relationship between them. Wow, as easy as that. So the first thing we'll consider here is how x varies with the first variable. Here in the first variable, it varies directly. So we'll write that down. X varies directly as y. So this is a symbol. This is a representation for x varying directly as y. And then the second one, x also varies directly as z. So and varies directly and z. This is it. So we could even say that y is also varying directly as z, as x is varying as y, and x is also varying directly as z. Y definitely varies as z. So what would I have here is just this. We'll just combine it. But this is not a joint variation, though this may look like, or they probably are somewhat similar. So we'll just combine it to have these. Okay, we said this already. Therefore, x varies directly as both y and z. So how do we represent this? We have this as x varies directly as y z. Mathematically, we have it as x equals ky z. It's just like you saying in a joint variation that x varies jointly as y and z. This is the same result it will give you as this combined variation of x varying directly as y and varying directly as z also. So now we can put in our parameters. X equals 3, y equals 4, and z is 5. So if I chip everything in, I would have 3 equals k times 4 times 5, and 4 times 5 is 20, so 3 equals k times 20. So making my k the subject of my formula, I will have it as k equals 3 over 20. So I've gotten k. Here we're asked to find the relationship between them. So I just need to bring out my formula again and insert my k into it, and I'm done. So from x equals kyz, where k equals 3 over 20, x equals 3 over 20 yz. And that's my answer. It's as simple as that. So let's show another example, something a little bit more technical. but it's the same thing as well because they are very easy to solve. So A varies directly as the square of B and also varies directly as C. When A equals 4, B equals 2, C equals 4 as well. Find A when B equals 3 and C equals 5. Okay, yeah, so we'll see how they vary across each other. It says here that A varies directly as the square of B, so you represent that out. We have it as this: A varies directly as the square of B, so the square of B is B squared, and A also varies directly as C. Okay, we have this here. So how do we represent it when they vary together? Because in this kind of combined variation, they have to work together. As one varies, another also varies. They are together. So joining them together, we have it as this: A varies directly as B squared and directly as C. So I have it here as A equals KB squared C, as simple as that. Then from A equals 4, B equals 2, C equals 4, put in your values. 4 equals K times 2 squared times 4. 2 squared is 4. So 4 equals K times 4 times 4, which is 16. Should have it as 16. So making K your substitute formula, I would have 4 over 16 as K, and that would be 1 over 4. So I've gotten my K, but I'm not done yet because I was asked to find my A when B equals 3 and C equals 5. So I'll continue from my formula: A equals K B squared C. I know what my K is already. My K is 1 over 4. So A equals 1 over 4 B squared C. Find A when B equals 3 and C equals 5. So let me put it in. That will be A equals 1 over 4 times 3 squared times 5. 3 squared is 9, as in 3 times 3. So A equals 1 over 4 times 9 times 5. So 1 times 9 times 5 gives me 45. So A becomes 45 over 4. As easy as that. We are done with this as well. Let's try a tougher example that would involve both direct variation and inverse variation. Here I have it. It says L varies directly as the square root of M and varies inversely as N. When L is equal to 3, M equals 16, N equal to 6. Find L when M equals 9 and N is 3. So here we have it as L varying directly as the square root of M. So let's represent that out. L varies directly as the square root of M in our direct variation. We know how it should be. It should be like this. Something like this. So L varies directly as the square root of M, and the same L varies inversely as N. It varies inversely as N. So here I have it also, which means the square root of M also varies inversely as N. That's what it means here. So we don't. There is no point going into that. So if we join them together, we'll have L varying inversely as N and directly as the square root of M. So bring in your equal to sign and then your constant of proportionality. L becomes K over N root M. So that's as simple as that. There can't be any combined variation tougher than this. So let's put in her values. L equals 3, M equals 16, N equals 6. Okay, so we have 3 equals K over 6 times square root of 16. The square root of 16 is plus or minus 4, but we need the positive 4 here. So let's just neglect negative 4. 3 equals K over 6 times 4. So I would like to cross multiply. If I cross multiply now, that gives me 3 times 6 equals K times 4. So that will be 18 equals K times 4, making my K my substitute formula again. I have it as K equals 18 divided by 4, and that would give me K equals 9 over 2. Cool. So let's move on to finding our other values. So find L when M equals 9 and n equals 3. Okay, so from my equation again, keeping everything, no time to waste, L equals now over 2 times the square root of 9, because our m is now 9, the new m is 9, and then our new n is 3. So have it as square root of 9. I need my positive answer, positive 3. 3 will cancel 9. I'll have 3 on top, and that will give me 3 times my square root of 9, which is 3. That's 3 times 3 over 2. So L equals 3 times 3 over 2. You can see my brackets here. So L becomes 9 over 2. So our answer here is 9 over 2. L equals 9 over 2, just as our K is. Wow, how fortunate. It's a coincidence though. Okay, so in our next video, we'll be treating partial variation. So if you enjoyed the video, please like and subscribe.